Hello everyone, this is Jim Staunton again, coming to you from Huntington Beach. We had some real excitement here a couple days ago. A freak kind of storm came through and dumped a bunch of hail on our beach, and the newspapers, actually the national news, carried pictures of surfers trotting across a white beach covered with what looked like snow. It was actually hail. That caused quite a stir around here. Well, I hope that by now you're well on your way to doing your papers. You have submitted by now your statement of the problem or hypothesis. You've had some feedback. You've done the first two chapters, review of the literature, as well as a statement of the problem. I reversed that. Statement of the problem followed by review of the literature. And now you need to start thinking about methodology. And one thing that we need to look at in terms of developing a methodology to either answer a research question or to investigate a hypothesis, maybe even a null hypothesis, is to start thinking about association and causation. Those two words just really can bedevil any researcher, and they have for years. So let me give you an example of what these two words mean and the effect they can have on a researcher. In the 40s and 50s, polio was a scourge nationally, well, probably worldwide as far as I know. Afflicted Franklin Delano Roosevelt. But more importantly, well, I shouldn't say more importantly, but more broadly, hundreds of thousands of children were affected. It caused paralysis and affected a number of lives. Medical researchers started to look into just what this was all about. They had no answer as to what caused it or why. But some researchers noticed that during warm weather months, the number of new polio cases spiked considerably. Well, someone put together that information, that spike, if you will, in a chart, along with ice cream sales of all things, and suddenly people were questioning whether or not ice cream itself was some sort of causal factor to young children contracting polio. Well, we know that was just silly and really never met any serious medical investigation. But it did highlight the point that while things can be associated, they may not have any relationship to causation. It's very natural for us to observe things. In fact, it's part of preserving our species that we look at things and see patterns. I can imagine tens of thousands of years ago, someone looking up in the sky and noticing on a regular basis this bright shiny object coming up in the east and setting in the west after a certain number of hours. Well, that phenomenon sparked the formula that the sun revolved around the earth. And it wasn't for, I don't know, thousands of years that that theory was disproven through scientific calculations. Let me give you I'm going to give two more examples. In the same line as our ice cream, Sal Kine has written a book called Statistics for Those Who Think They Hate Statistics. It's on the recommended reading list. It's kind of a fun little read. His example is a Midwestern sheriff in a small town who notices that every summer home robberies skyrocket. And as he's going through town, he notices a long line of people outside the ice cream shop. He concludes that there has to be a connection between sales of ice cream and home robberies. So he shuts the ice cream parlor down. The robberies go down. He concludes he's done a great job by shutting down the cause of the robberies. Well, you look at that and know that it's really laughable, but you have to ask yourself, were his results reliable? Could he repeat this over and over again? Open the ice cream parlor during warm weather months and burglaries go up, shut it down, burglaries go down. He's done a test that is reliable but clearly not valid because it has nothing to do, the ice cream, with the fact that during warm summer months people leave their homes, oftentimes unlocked, and thieves take advantage of it. The last thing I want to do is point out what I consider to be an absolute tragic example of the confusion between association and causation. It happened again in the 40s and 50s. Doctors across the country noticed that people who smoked tended to develop a certain type of cancer. And so they started writing scientific papers in peer-reviewed journals, and they said smoking is related to cancer, the development of cancer. Well, the tobacco industry was not about to stand for that, and so they brought in, and I've read that there was one specific expert who wasn't even a medical doctor, but who was well-versed in research methods, who said, hold it, you haven't drawn any relationship between the act of smoking and the causation of cancer. You haven't shown or proved that one causes the other. How do we know that it's not air pollution from other sources? How do you know it's not genetic? How do you know it's not some other causal factor? Well, the medical community and researchers involved in that type of work realized that they had to prove an actual causation. Unfortunately, through very stringent laboratory tests, through the isolation of certain chemicals, they were able to isolate the chemicals, inject laboratory mice with those chemicals, and sure enough, we saw that smoking does cause cancer, and after years of fighting, the tobacco industry finally gave up. But sadly, tens of thousands, probably hundreds of thousands of people died painful deaths because one industry was able to say, you haven't shown causation, therefore you cannot prove anything. All right, let's give one solid example before I end this video. Let's suppose you've observed that Olympic weightlifters, people who are doing these deadlifts with very heavy weights and really large amounts of weight, have developed their calves and thighs very, very well. And you think that maybe well-developed calves and thighs are associated with the ability to improve vertical leap. And so you devise a test. The intention is to show that these heavy lifts, this kind of weight lifting, can show that it will result in a change in vertical leap for volleyball players, basketball players maybe, perhaps wide receivers in football, maybe outfielders in baseball who have to make leaps against the fence to catch fly balls. You want to improve vertical leap. So you get a group of test subjects. They should meet the standard of at least 30 and preferably more, and you put them through a regimen in which they lift heavy weights, slow reps for a certain amount of time, let's say a month. You test them beforehand to see their vertical leap, and you test them afterwards to test their vertical leap. You conclude Olympic weight lifting with the heavy lifts, slow reps will improve vertical leap. Have you shown or proven your theory? Well, if I were to look at the results of a study like this, I might ask what controls you put in place to see to it that your test group was as perfectly matched as possible. Were they all the same age, type, height, weight? Secondly, I might ask what factors might intervene during your test period that could pollute your findings. For instance, did you control for steroids, use of other chemicals to improve performance? If you haven't, you could pollute your findings. Finally, while you may conclude that the lifting made the difference, was that really the case, or was it subtle or maybe even not so subtle changes in the muscle fibers in the calves and thighs themselves? Finally, you would have to guard against another research coming along and saying something like, well, you know, I got those same results by using elastic bands. It's cheaper, easier, and the risk to the knees is much less. These are the kinds of things that any researcher wants to guard against and look for when drawing conclusions from a methodology. I hope this helps. At least I hope the stories have been entertaining, and I'll get back to you with another video shortly. Take care.